Today, we will just do a little review for the topics that are calculus specific for the exam. So we really only have two areas that are potential for the exam. The first one is finding the center of mass or the moment of inertia of a solid object. And so the equations are basically just the one shown here at the bottom. The equation for center of mass is the integral of x dm, where dm is a little piece of mass in your object. Then you have to integrate over the entire object, divided by the total mass, which of course, integral of dm by definition would be the total mass. Moment of inertia is the integral of the distance perpendicular to the axis of rotation squared times dm. So you integrate, once again, dm is a little tiny piece of mass. You have to integrate over the entire mass of your object. And then those dm's, since they're little tiny pieces of mass, we usually do spatial integrals. Sorry, I'll turn over here further. We usually do spatial integrals. And so if it's a one-dimensional distribution, dm is lambda dx, where lambda is the lineal density, the mass per unit length. So I didn't write that down here, but in these definitions below, lambda is the mass per length, sigma is the mass per area, and rho, of course, is the mass per volume. So you're just using whichever one is appropriate. In all cases, it's density, d, and then whatever your space is for, three-dimensional volume, two-dimensional area, or one-dimensional distance. So depending on your situation, you may do any of these. So I will introduce the next topic and then do some examples. So the next topic here is three topics from liquids. What we did in class last week, finding the pressure by integrating that dP is equal to rho g dx, where dx is a little piece of vertical depth. And that's very simple if the density is constant. If the density is changing, it becomes more complicated, of course. dF is pressure dA to find the total force. Remember, with the dam, we calculated the total force on the surface of the dam due to pressure. And then finally, calculating the d torque is R cross dF. And so we calculated the torque about, I think we did the base of the dam. I don't think we ended up doing the top of the dam because of time last class period. But you had to have the R cross dF. So your calculus question will be one of these. I actually had to toss out what would have been a good question because I hadn't talked about it previously. I didn't want to talk about it in class today and say, so be ready, because that could be it. But it was a question that said, given height is equal to it had numbers, but I'm just putting ax cubed plus bx minus, bx squared minus cx plus d, something like that. It said find the position closest to the origin where you have a stable equilibrium. So basically, it might have said more, but I think that was it. And you have to imply, that means I have like a marble on the ground, and this is the elevation function. And where's it going to have stable equilibrium? So if I'd given you that question, would you have known how to treat it? Maybe. How do you find stable equilibrium? What's the definition for stable equilibrium?
A little bit of displacement doesn't cause it to go, it just returns, right?
Okay, a little bit of displacement, it comes back. In terms of potential energy, what does that mean? It's in a potential energy well. And you probably have heard that term potential energy well in things like chemistry as well, right? And so we have to find the potential energy function. Well, what's the potential energy function for gravitational potential energy? MGH. It's one of those really hard ones. MGH. And so how do we find a minimum? Well, we have to do both. We have to do the first derivative to find maxima or minima, and then the second derivative to determine which one it is. So we have to do two derivative tests. So find extrema. Extrema is the plural form of extremum, which means a maximum or a minimum. So this is the word that means find the maxima and the minima. Perfect. So the first is to find the extrema by setting that derivative equal to 0. Now I told you this is actually not going to be on the test because I didn't want to introduce it and then say, haha, I'll be ready for it. So first step, multiply everything by mg to get mgh, which means I'm going to have an mg that I can factor out. And of course, the derivative is very simple, right? The method is what was important to remember because derivative of ax cubed is just going to be 3ax squared plus 2bx minus c. And so I solve this. How many answers do I get? How many solutions do I get for that? 2, right. So I'm going to get 2 solutions. Hopefully one of those is a minimum. And I say hopefully, you know there's one of them a minimum, right? It wouldn't be possible for them to both be maxima. It could, yeah. Anyway, so just saying that equal to 0, I would have huh?
Because the coefficient of the second term is 2b, not just b.
Where did I? Oh, right. It should. That's where I made the mistake, and hence everywhere. I'm going to put the 2 and put the parenthesis here just so we don't forget the form. Thank you. I didn't copy right, which means I didn't do right after that. So this, of course, if you have the numbers, you would put the numbers in and get your answers there. For the 2 cases, and then to see if it's a maximum or a minimum, the last step is second derivative. So the second derivative is mg times 6ax plus 2b. And so we'd put in each value of x. Now, obviously one of those values of x is going to have to be a negative and one a positive, or these would both be the same sign. But you put in your values for x, and if the value for x is a positive value, then that means you have the smiley face. If the value for this derivative when you put in the x is positive, if positive, then it's concave upward. If negative, then it's concave downward. So the negatives are going to be maxima, the positives are going to be minima. So that would be how you would have solved that problem. It would have required you to do both tests, not just one, because you need to find which extrema were minima, and then find the closest one. And, you know, it might have had, in fact, I'm pretty sure it had x to the fourth, so you would have the potential for 2 minima, whereas here you didn't have the potential for 2 minima. You only had 1 minimum possible. Excuse me. Okay, so that's not on the test, but it was something that I felt that when I looked at it, yeah, I should have covered that just a little bit, you know, how you can define if it's stable or unstable. Or if it was neutral, how would you find the neutral equilibria from this problem? Okay, neutral means that the slope is 0. And so we found slope 0 for equilibrium. If the second derivative is 0, it's going to stay at 0, at least for a range. And so that would be your test for neutral equilibrium, would be if the second derivative is 0, it's neutral. So second derivative being positive was stable, second derivative being negative was unstable, and second derivative being 0, neutral. Okay. Any questions before I go to actually example problems? I've only spent 10 minutes. I've covered the names, the words for review, so the problems will be all I have left. Question before I do problems? All right, let's dive right in. So examples of center of mass problems. So I have 3 examples here: a 1-dimensional rod, a 2-dimensional rectangular sheet, or a 3-dimensional sphere. And we can actually do these pretty quickly. They're not long and drawn out problems. So let's just do number 1, the rod. So here I have x equals 0. Here I have x equals L. And the density of the material is dropping off exponentially. And so I'm going to have x center mass is equal to the integral from 0 to L, because that's dimensions of my rod, of lambda dx. Lambda has lambda 0 that's constant. So I'll bring that outside. E to the minus x over L dx. Well, what's the integral of e to the minus x over L dx? You divide by the derivative of the exponent, right? So I'm going to divide by negative 1 over L. Put in my limits. Notice, divide by minus 1 over L is the same as multiplying by negative L. So that's going to be minus lambda 0 L. And then putting in the limits, I have e to the minus L over L minus e to the minus 0 over L. Did I make a mistake?
Question, how did you get 1 over L?
I divided by the derivative of the exponent. So since the exponent is minus x over L, I divided by the derivative of that, which is minus 1 over L. Question ready?
What initial equation did you use for x in your terms?
What? The one from the first slide here. I'll go back to it. Right here. Except for I forgot to put the divided by integral of dm, didn't I?
Okay.
Is that what you were?
Yeah.
I made 2 mistakes. Okay, I'm going to start over because the other mistake is much more significant. Well, I can do this. I just have to change what I claim I'm solving for. Because I forgot to put the x in there. Mass is equal to. Everything I do would be correct if I solve it for the mass. I forgot to put the x in. And so that's my mass. Of course, this is going to be equal to lambda 0 L times 1 minus e to the minus 1. Because minus e to the 0 is minus 1. I had the minus out front. That's what made the plus 1. And then e to the minus L over L, well, that's e to the minus 1. So bringing this my sign. So that's the mass. I am glad you corrected me because my errors were larger than I had anticipated. So that's the bottom part. Now, I'll change color actually. It's integral of x dm or lambda dx over the mass. So that's the integral from 0 to L of x e to the minus x over L. Question? Please don't say I made a mistake again.
Should it be e to the minus 1 minus?
Over here?
Yeah, because you have on your right side e to the minus 1, or sorry, your left side e to the minus 1, and then the right side becomes.
Okay, I'll write out the step in between.
You repeat.
Oh,
Modern
he distributed the
Yeah.
negative sign. Okay.
So e to the 0 is 1. And so I just took this minus and minus and put that term first.
Okay.
Factor back out the lambda L's. And I have 1 minus e to the minus 1. Okay, it's better to understand than to say, oh, maybe it's some voodoo I don't know. After all, you've seen I make mistakes. Right. Okay, so now I have to do this integral. How do you do that integral? I don't have it memorized. Integration by parts, yeah. So I'll take this integration by parts and I'll say let u equal x, therefore du equals dx. Let dv equal e to the minus x over L dx. Therefore, v is equal to minus L. How do I get that v? From the integral that I just did right there. Right? I already did the integral of e to the minus x over L dx. And so I just put that in because I already did it. So now that I have this, I can put xcm is equal to my u times v. So that's going to be minus xl e to the minus x over L. My limit's from 0 to capital L. Minus integral of v du and we have more calculus to do. Hooray. When I do this integral, it's again the same integral, e to the minus x over L. And so I know that's going to give me, I forgot something, didn't I? Yes, I forgot the lambda zeros. And I'm out of space. The way to cheat when you run out of space. So this first term is unfortunately, the pin stays the same size. Minus L squared e to the minus 1 if I put in the upper limit. And if I put in the lower limit, it's going to be plus 0 e to the 0, which is just 0, right? Because e to the 0 is not infinite, so we don't have a problem with L'Hopital's rule. So there's my first one. Then minus over m. And that integral is going to have another multiplied by minus L. So a plus L squared. When I put in those limits, that's going to have the upper limit is L squared e to the minus 1. The lower limit is L squared e to the 0. And so putting all of that together, all over, and what did I get for M? Oh, I forgot the lambdas again. It's good that there's a quick fix for that. So the lambda zeros cancel out. 1L will cancel. And I'm going to have L times 1 minus 2 e to the minus 1 over 1 minus e to the minus 1. And I fit it all on one page. You're asking what the final answer was there? I can actually write the final answer bigger over here. I'm going to do it. L times 1 minus 2 e to the minus 1. So, hooray! So that's the first of these problems. The second one, a rectangular sheet of length L and width W with a areal density of sigma equals sigma sub 0 times xy. So to do that, I'm going to have to create a new sheet here. Page manipulations, insert. Putting in 3 sheets, but none to the wind, just for the record. So in this case, I have a rectangle that has dimensions of my y's look very nice. Has dimensions like that. And I want to find the center of mass. Now in this case, the center of mass is going to have 2 components, the x component and the y component. And so when I do this, I'm going to have my x center of mass is equal to the integral of x times sigma dA over the integral of sigma dA. And the y center of mass is equal to the integral of y sigma dA over integral of sigma dA. So let's break these things down to make them as easy as we can. So I have basically 3 integrals to do here. So let's just do those 3 integrals as separate integrals and then combine things. So first integral of sigma dA. For a 2-dimensional space, what is my dA going to be using Cartesian coordinates? Dx times dy. So that's going to be equal to the integral of sigma sub 0 xy dx dy. Well, I'm going to have two integral signs, right? One for the x, one for the y. So this generic integral becomes two integral signs, one going from 0 to L, one going from 0 to W. And then this integral is actually real easy because I can completely separate it. Whenever you can separate it so that you have this portion only has x and this portion only has y, then it's just two regular integrals that are not dependent on each other. So I'm going to write this as separated integral from 0 to, put the sigma 0 outside, 0 to L, x dx, integral 0 to W, y dy, right? I just did the two integrals separately. So simple. Hooray. Divide by 2 is divide by 4. Sigma 0 over 4 times L squared W squared. So that's my mass. Now for the x1, I'm going to have my second integral here. Integral of x sigma dA is equal to the integral of x sigma 0 xy dx dy, which once again is separable. So this isn't difficult. So you plug in your values. 2 times 3 is 6, so it's divided by 6 instead of divided by 4.
From that, you can really easily tell what the y integral is 2.
Because of the symmetry I chose, you're correct. Because of that, my y integral is going to look exactly the same, except for it's going to be L squared W cubed. And so I will just write that out. And so then my x center mass is equal to sigma 0 L cubed W squared over 6 over sigma 0 L squared W squared over 4. We cancel all that we can. Sigmas cancel. 2 of the L's cancel. Both of the W's cancel. And we're left with 2/3 L. Right, because 4 over 6 is 2 over 3. Sorry, I probably should have. There. 1 over 6 over 1 over 4L, which is equal to 4 over 6L, which is equal to 2/3 L. So that's my x center mass. And because of the symmetry that was noted by Jonathan, what's my y center mass going to be here? It's going to be 2/3 W, right? So because of my function, this was a lot easier than the last one, right? Depends. The difficulty in doing the math depends on the function. I thought I chose the easy function for the last one. Yeah, I didn't choose the easy function I thought I had, which is kind of unfortunate for the spherical one, right? Wrong. Why do I say wrong? Let's do the spherical one as an exercise. If I have a spherical distribution of mass that only varies with the radius from the center, what can you tell me about the center mass? It's got to be the center, right? So we're doing this as an exercise because we know the answer just based on symmetry. And many times in a problem, you can just say, based on symmetry, boom. You know, yes, you can. I mean, you can't say boom, and you have to identify what the symmetry is. Gabriel's very disappointed with me.
If we include the symmetry part, can we include boogie as well?
Yes, yeah, okay. You can do that. No, in very, very seriously, physicists solve a lot of problems by utilizing symmetry arguments. Things like if you have the integral of an even function over symmetric limits. An even function is one where you have like an even exponent so that it's symmetric on both sides. Then if you have an integral of an even function over symmetric limits, it's the same as 2 times the integral from 0 to the limit. But if you have an integral of an odd function, something that's anti-symmetric about the origin over symmetric limits, it always has to be 0. And so we never do those integrals. We say by symmetry, the integral of an odd function over symmetric limits is 0. We save ourselves a lot of work. So identifying symmetries, next semester when we talk about using Gauss's law, it's going to be a whole lot of identifying symmetries. And we actually won't do much calculation, actual calculation. We'll do identification of symmetries there. So even though it's calculus, you don't actually do calculus. You identify symmetries to say, oh, well, it must be this thing. Okay, so for the sphere, okay, that looks like a circle, but just imagine that I had the artistry to make that into what looks like a sphere. You guys imagining? We have a spherically symmetric distribution with rho is equal to rho watt e to the minus, I put r over r0, right? So this is a situation just like with our rod where the density is decreasing with distance. So it starts most dense at the center, gets less dense as you go out until you get to the edge. Exponential decay of the density. So if I want to find the x center of mass, I need to find what my x variable is in terms of the spherical coordinates, or I need to find what r is in terms of x, y, and z. I have 2 ways I could do this. Which one do you suppose is going to be easier, to convert it to Cartesian coordinates or to keep it in spherical coordinates? Keep it spherical is the correct answer. The reason for that is the limits are simple. If you convert it to Cartesian coordinates, then you're going to have integral with respect to x, integral with respect to y, and integral with respect to z. And the first integral you do, for its limit, the limit is going to be a function of the other 2 variables, right? Which is kind of a nuisance. And then the next one will be a function of the remaining variable, again a nuisance. And then the last one will actually be the one with the simple limits from 0 to, or well, actually minus r to plus r. But your limits become a complicated process if you want to convert it back to Cartesian. That's why we, if it's spherical symmetry, we stay with the spherical coordinates. So in that case, I need to find what x is because I have this integral of x rho dv over the integral of rho dv. So to find my x component, I'm going to have to take into account what the coordinates mean. And I think I have the coordinates on the first picture. Oh, no, I chose a different picture. I had 2 I was choosing from. And okay, darn it. So for my coordinates, the 3 variables for spherical coordinates are theta, phi, and r. And so phi goes from 0 to 2 pi, it's going all the way and around the circle. And so if I can find my projection in the xy plane, then I'll use phi to find how much is x. So I think I'm remembering here's my angle phi going in the xy plane. But I have something that's actually 3-dimensional, so it's somewhere going up here, and it has an angle of theta right there. So how do I find the amount of my total radius r that's in the xy plane? Well, actually, let's start with the easy one. Let's find the z coordinate. How do I find how much is vertical if I have an angle theta between vertical and my vector? Yeah. My picture is going to be like this. Here is my variable r. Here's my angle theta. So it's just going to be the adjacent side, so cosine theta. So that gives me my x component. Now for y and z, my radius in the, or not y and z, x and y, my radius in the xy plane is going to be the opposite side of that, which is r sine theta. And so that means to find my x component, if this red part is, r sine theta, then the x component will be cosine phi of that. So I will have and finally the y will be and so those are what I have to put in for finding the x component, the y component, and the z component. So now finding my x center mass, there was no R0, it's just capital R. And then I have one more piece. What's that last piece that I have to write still? That before I put the divider. What's the last piece that goes in the numerator? My dv, which is r squared sine theta dr d theta d phi. Yeah, it's on the equation sheet, but that's what dv is for spherical coordinates.
Normally, in spherical coordinates, you use phi for the azimuth on the z, and then theta for the x and y plane.
I didn't catch what you said.
In spherical coordinates, isn't it normally that theta is like the polar point, the x and y, and then z?
I thought it went this way. It makes a difference in my answer if I have it backward.
I remember it this way.
Yeah, look it up, because if it's going to make a difference in my answer quite clearly if I have the limits wrong and the sine and cosine wrong. So I will wait for him to look it up here just because it makes a world of difference. And I should know the difference in theta and phi.
Oh, it's different. Yeah. Is it different in physics or math? That makes sense. In math, phi is from z, and in physics, theta is from z. Theta is the... Okay.
Okay. That's not comforting, actually, is it? Not at all. Okay, so that's my numerator. My denominator is going to be integral of rho naught e to the minus r over r. Oh, these are going to be fun integrals, especially because we know the numerator is going to have to give us 0. It seems like a lot of work when you know the answer is 0. That's why we say symmetry demands it. But if I look at this, I'm going to have on the top r cubed. So let's just look at the top. Integral of r cubed e to the minus r over capital R dr. That's going from limits of 0 to capital R. Then integral from 0 to 2 pi of cosine phi d phi. Integral from 0 to pi of sine squared theta d theta. So there's my numerator integral. if I look at these, this one right here is going to be 0. Because I'm integrating a sinusoid over a complete cycle. And so I'm not going to spend my time looking at the others. Now, you notice this one here at the end, sine squared theta, that also is going to come to 0 because, or excuse me, no, sine squared can't come to 0. It's always positive. My bad. It comes to, I think it's 1/2, but this one comes to 0. So the whole thing is 0. And if we do the y now, what's going to change for phi? The only thing that changes is you change from cosine phi to sine phi. If I do an integral of sine phi from 0 to 2 pi, what's that going to give me? Zero as well. So we have 0 immediately by looking at the top integrals for the x and y. So now we only have to look at the z. The z doesn't have any phi in it, but it has cosine phi. So what I'm going to have is for the z on top, oops, not equals, times. The last part, integral from 0 to pi of sine theta cosine theta d theta. Sine theta cosine theta is, does anybody know what that turns out to be? It is I think it's sine of 2 theta, I think 1/2 sine 2 theta, something like that. And so if I do sine of 2 theta from 0 to pi, that's the integral over a complete cycle. And so in this case, this one here is going to go to 0. And so I didn't do any of these integrals. Some of them would have been easy, right? Integral from 0 to 2 pi of d phi, that would have been easy. One of them I would have done just 3 times, but integral of r cubed e to the minus r over r. If I don't use an integral table, I'm going to have to do integration by parts 3 times, and I don't want to.
So we're talking about the z being for phi or for theta, and in your example that you did the moment of inertia last week,
Yeah.
I think you had them switched.
Did I?
Because you have 0 to 2 pi, the limits for d theta, and you have theta here instead of phi.
Really confusing that there are 2 different.
Yeah.
Okay, it is confusing. I shouldn't have made a mistake last week, but if I made a mistake, one of the 2 is clearly a mistake having them. And last week I actually did look up what the coordinates were before class.
Okay.
So last week's has to have been the correct one,
So it should
Which-
be theta and phi.
which would mean that it would change theta and phi. This here I still used that, but I had the theta and phi switched. So, it's embarrassing. I should have looked this up.
So I have the Wikipedia page on it pulled up, and I don't know, it says that physics uses it the way you have it now, but math uses it the other way. So I mean, they're both proper, just
They're both proper, but you have to be self-consistent within a problem. And in physics, we always use this here for dV. And so that goes with a specific definition. And in the last lecture, was it the last lecture or was it 2 ago? Yeah. Let's just pull that up so we can look at the picture, because we only have 5 minutes left, and it's more important to get this squared away than to okay. So 2 weeks ago, yeah. Okay, that was cylindrical. Okay, so here's spherical. And you see the dv is r squared sine theta d theta d phi, and that goes with having phi in the xy plane and theta being the vertical angle. That is what I did today, so I did do it right today. Now I can feel better about myself for a short moment.
Your work though for it, because I just copied down what you had done for your work on that one. Or like I followed along what you were doing.
I didn't have any work there. If you were referring to this picture, this is cylindrical coordinates.
Oh.
Okay, so the bottom line, I can breathe easy. I did not make a big, huge error in today's lecture. Because, that's one of the things I fear. Okay, where are we? So we've gone through and we found correctly why the moment or that center of mass is the center using the spherical coordinates. Now, the last thing I had here was now find the moment of inertia about the center of mass. Well, how do you find the moment of inertia? You need that r perpendicular. And so for the one-dimensional case, of course, if we're doing about the center mass, I wasn't very specific. If I do it about the center mass for the first one, I could be doing it down the axis or some other angle. What I meant was the axis that's perpendicular to the rod. Right? I should have been more clear. And so I would just have my r perpendicular is going to be, x, if I put x equals 0 at the center of the rod. Of course, I wouldn't put x equals 0 at the center of the rod, so instead I would have to use r perpendicular is equal to x minus the center of mass x, or absolute value of that. It's going to be squared, so it's not going to be a problem, but you have the center mass was some specific position, and so there's xcm. And so if I have an x that goes out to here, then my r perpendicular is this distance. And if it went to the other side, if it went out here, then I have r perpendicular is equal to x minus xcm. So the truth is that r perpendicular is the absolute value of xcm minus x, because it depends on which side you are, and r is always positive. But since it's r perpendicular squared, you don't have to worry about it, because the absolute value sign is going to disappear when you square it. It's always positive when you square it. So I just can take either one of these for the r perpendicular, and I square it, and I just have the one integral. Is that integral going to be easy? Going to go with no, because it's going to have an x squared term, an x term, and a constant term, all multiplied by e to the minus x over L. Right, so we're clearly not going to finish that in a minute. For the rotational one here, we once again found that the center of mass for our system was 2/3 in each direction. So there was our center of mass. And then your r perpendicular, if you have, here's your x and here's your y. Okay, so here's x, here's y. That works better. Then you have to calculate this distance. So you're going to have to use the Pythagorean theorem. So you'd have r perpendicular is equal to the square root of x center mass. Well, x center mass we know is 2/3 L minus x squared and so that's what we would have for the r perpendicular there. Of course, r perpendicular squared, it comes out to be just a long polynomial for our integral here, but it's going to have many terms. The one that's the most difficult, though, is the sphere. Because for the sphere, my r perpendicular is now going to be, well, let's do it about the z-axis because of symmetry. The r perpendicular will be what we called the rxy when we were resolving to find what x and y were, which was r sine of theta. And so now our integral is going to have integral of r sine theta quantity squared times r squared sine theta d theta d theta d phi d r. And so we'll have that longer integral to do. We're a minute over time, so I'm spared any of the hard calculus here.
So this would be on the test today?
You won't have any problems that are as long in the math, right? It depends on what the function is for, for your density. If it's going to be hard or easy. And you won't have ones that are harder, like, e to the something. But you can certainly have ones that have, like, the density is just a linear function in x or something that's a simpler integral to do.
So just find center mass and then find moment of inertia.
I would do one or the other.
Okay.
There's one that has spherical coordinates. Will it have the coordinates labeled in the problem?
If it has spherical coordinates, that's a good question. If it has spherical coordinates, I will, I'll give you that, especially because of confusion today.